Okay, in this video we're going to look at calculating the torque exerted by non-perpendicular forces. So a quick recap of what we've talked about primarily so far. We've seen that if we have a force exerted on some rigid body and there's a point of rotation of that body, in this case let's say the end of this board, and the force does not go through the point of rotation, but rather acts at some distance away, which we call r, the lever arm, so the vector from the point of rotation to the point of contact of the force. What we've seen is that that force exerts a torque. And the way we calculate that torque, let's just call this torque 1, is by figuring out the perpendicular component of the force, which I'm going to call F1 perpendicular, and we multiply that by the lever arm. Now this works for forces where the angle between the force and the lever arm is 90 degrees. Now what happens when this angle is no longer 90 degrees? How do we calculate the amount of torque exerted by that force? Now I'm going to show you two different ways to do that from the sample problem that I stole from the problem set. So here we have a wheel. It has a certain diameter, it has a certain radius. Let me just call those D and R. And we have two different forces exerted by two different people. I believe this is a merry-go-round in the problem. So we have Jerry exerting a force at this point. The point of contact is an important point, and we have Tom exerting a force at that point of contact. And if what you should see right off the bat is that these forces are now at some angle less than 90 degrees to the point of rotation. If we take the center as the point of rotation, this is a fixed axle, therefore it'll be forced to rotate about that point. So the first way is to take the point of rotation and draw the lever arm for the force, and I'm going to call this R sub j. R sub j will be the vector from the point of rotation to the point of contact, or the point of application of the force that Jerry exerts on the merry-go-round. And what I would need to do then is take Jerry's force and figure out what is the perpendicular component relative to the lever arm. So I'm going to draw that as this component of the force, Fj perpendicular, and then I would have also Fj parallel. So I can break Jerry's force, let's call this Fj, the overall force, into a perpendicular and parallel components. And what I would see is this is the component that exerts a torque. This exerts zero torque because if you look at it, it's through the point of rotation. So any force through the point of rotation exerts no torque. So then I just have to calculate what is this perpendicular component. So based upon the geometry here, this is 80 degrees, therefore this is 80 degrees. I'm going to call that my theta. And so Fjt is F sub j sine of theta, or sine of 80 degrees. So I take that component and I say now the torque exerted by Jerry is just the perpendicular component of his force, Fj sine of theta, times R sub j, or the lever arm distance from the point of rotation to the point of application of the force. Now in this case, this would be a clockwise force, so therefore when I sum the forces about the center, this would be a negative torque. Now I'm going to show you one other way to do it, and I'm going to show you, prove to you that these are mathematically equivalent. So the other way to do it is to look at the force and to take the line of action of the force. And all the line of action of the force is an extension through the force of a line, kind of before and after. So the force is acting in this direction, so if I take a dotted line through that force, that's the line of action of the force. And what I'm going to do now is I'm going to draw my lever arm from the point of rotation, and I'm going to draw it so that it makes a 90-degree angle with the line of action of the force. So that angle is 90 degrees. And all I'm going to do is say whatever this lever arm is, so the torque exerted by Tom, so this is, let's call this F sub t, and I'll say the torque exerted by Tom will be the force exerted by Tom times this new r sub t. But notice this r sub t is less than the actual radius of the circle because it intercepts the force before it reaches all the way over. So we have to figure out, well, what is r sub t? So if we do a little geometry here, what we notice is this would be r, the distance here to here. This would be 60 degrees here. And so based upon the geometry of this, the sine of 60 degrees would be this r sub t over r. So r sub t would be r sine of 60 degrees. And now let's just go into our general notation where this is my theta. So I'm going to substitute in here then the torque exerted by Tom is Tom's force, Ft, times the radius of the circle, r, or the distance from the point of rotation to the point where the force is applied on the outside, times the sine of the angle in between them, which is the sine of theta. And lo and behold, what we have here, if we compare these two methods, are mathematical equivalents, right? Whether we look at it from the perspective of the perpendicular component of the force, so take the angle in between r and the force, calculate the perpendicular component, and then multiply by r, which is Fj sine of theta times r. Or we take the lever arm and draw it straight to the line of action of the force, so it's perpendicular, and then calculate that shorter length. It's still the radius of that circle or that lever arm times sine of the angle between them. So times the force, the magnitude of the overall force. So either way you go about calculating this, you end up with mathematical equivalence. So whenever you have a force that's exerted at an angle that's less than 90 degrees or greater than 90 degrees, so long as it's not perpendicular, you find the perpendicular component, multiply by the lever arm, or draw the lever arm to the line of action, find that length, multiply by the force. Either way, you get F r sine of theta.